Hello and welcome to the lecture on elasticity, stress, and strain. So basically this is all about deformable solids and understanding the forces and pressures at play. Okay, so these are some of the pictures we're going to consider. Things that are changing length, things that are getting sheared, also things that are getting compressed in all dimensions. So let's get to quantifying this and comparing it to things we've seen before. Okay, so we can see we have a lot of terms here that involve a modulus. This is a material-specific value. Now let's take a look at it. So first of all, the units of the modulus, and this the first one we look at called the Young's modulus, have units of force per area, newtons per square meter. We've seen that before because this is the units of pressure. All right? So this is actually a type of pressure, but again, it's a constant that is material specific. You look it up on a table for, say, concrete or rubber or steel, okay? But it does have units of pressure or force per area. Okay, so it's a material specific quantity that relates force to extension or contraction. So things getting longer or shorter. Okay, like shown here. Here we have an example of tension creating an extension, right? And we can see with the dotted line that this rod or cross section of a wire or something has gotten longer. And then we see compression where there is actually a shortening. Okay. All right, and it's also called, and this is the term that I tend to use, the elastic modulus, okay, because it does have to do with that elastic behavior, stretching and compression, okay? If we look down here, we can see, and we'll talk about this graph more, but we can see that the slope of the linear region, also called the elastic region, appropriately, is none other than the Young's modulus. And that's because this graph is a graph of stress versus strain. Okay, so it's stress as a function of strain. It's how much force is in the material, okay, as a function of how much the material has changed length. All right, and this is an absolute change, but this is a fractional change because it's change in length over original length. The units of the vertical axis are dimensionless because it's a ratio, the horizontal axis, and the units of the vertical axis are none other than, well, pressure again, or force per area. That means that the slope also has units of pressure, or force per area, and the slope is the elastic modulus, the Young's modulus, okay? And that's the linear region, the elastic region. And region is just a term given to a part of a graph before that graph changes, because obviously once the graph starts to become curved, it's no longer linear, so that's why we talk about different regions or different ranges, okay? All right, and this is what's called a stress-strain graph, which is really kind of the cornerstone of talking about deformable solids. We can represent them, visualize them on stress-strain graphs, such as the one shown here. Okay, but let's get to other types of deformation, the other two, shear modulus and bulk modulus. Now, to be fair, there's actually other, including torsion, which is another type of deformation, but the only other ones we're going to cover in this class are shear and bulk. Okay, so what is the shear modulus? Well, again, it's a material-specific quantity that relates shear force to extension, all right? So it's this. It's pushing a force parallel to a cross-sectional area and then having the shape deform at an angle like this. That's shearing. That's like taking a large book and like pushing on the cover of the book and having all the pages kind of come out in a sort of parallelogram shape. Okay? That's what's happening here. The last one is the bulk modulus, another material-specific quantity that relates pressure to changes in volume. Okay? So in this case, we're actually concerned about the volume changing rather than just one dimension that's parallel to the direction of force and perpendicular to the cross-sectional area, or a one direction that is parallel to the applied force and also parallel to the cross-sectional area. Okay, but in the case of the bulk modulus, the force is omnidirectional. Okay, so it is force coming from all directions. So there's not one axis to consider, unlike these two cases, but instead the whole object is getting compressed. Its volume is changing. Okay, so it's the only modulus where we're going to see a volume change. Okay, and we're going to see all the moduli show up in the only three key formulas for this lecture. Okay, but we'll get there in just a minute. So let's make sure we're clear on the difference between elastic and plastic, okay, in the context of deformable solids. So elastic is reversible deformation. It would be this region here shaded in yellow. Okay, it is the linear region. Plastic is permanent deformation. So plastic means permanent, okay? And it is a region here highlighted in pink. So if you deform a solid up until the plastic region, you have permanently affected sort of the molecular bonds and the structure of that material. It will not return to its original length, okay? And so there is a yield strength that separates the two ranges, the plastic range from the elastic range, or the elastic range from the plastic range. And there's also a final stop where the plastic ends because there's rupture, there's failure of the material, all right? So tension and compression are just changes in length. They would apply to, you guessed it, the Young's modulus, also known as the elastic modulus, okay? So what's the difference between yield strength and ultimate strength? So I mentioned it just a second ago. So yield strength is the stress value, remember stress is force per area, at which material transforms from elastic to plastic. Okay, so that transformation from linear to nonlinear is the yield strength. So it's whatever the vertical coordinate is where your graph transforms from linear to nonlinear. The ultimate strength is the stress at which material breaks. So the ultimate strength would be right there. It is the rupture value. The rupture is more like a coordinate because it would have both a strain and stress value. But then if you want to talk about the ultimate strength, strength implies you're talking about, well, the vertical axis, values of pressure, force per area, values of stress. Notice the terminology here. You got to get used to the terms that we use. Stress here is again, it's a pressure, but we call it stress in the context of deformable solids. All right? Okay? So there's some of our key terms out of the way. Fracture and rupture, exactly what you expect. It is the quantity of energy material can absorb before it breaks. Okay? All right? And toughness is represented by the area under the stress strain curve. And that's shown right here. Okay? So here we have this actual green area is the toughness. Okay? It is the area under the stress strain curve. And the toughness of a material is not always the same as its ultimate strength. So you could have a material that is very tough because it has a large area under its curve, but it's not very strong, and vice versa. Okay? All right, let's get on to the key equations and then some practice. All right? So here are our three key formulas, and you can even see we have three types of problems. They match up, and indeed they match up with the three moduli. So that's the whole takeaway here. We've got stress, we've got we've got the elastic modulus, we have the shear modulus, and we have the bulk modulus. Okay? All right, so first of all, stress and strain. Okay, so the key characteristics. You can really think of stress as force normalized by area. So force normalized by area. And when you say something is normalized, that means you've divided by that quantity in order to get rid of it. Okay? So when we normalize by area, we eliminated the effect of the area. That means we can talk about the stress of an entire material without actually caring what size the sample is. This is very different than, say, the spring constant, because the spring constant was unique to every single spring. And if you changed the diameter of the spring, you'd have to have a new spring constant, because it wasn't material specific, it was object specific. Okay? So certainly there's a real utility here to having something that is material specific. So, but the comparison between stress and the spring constant are obvious. Okay? Or I guess a more apt comparison is the comparison between this quantity here, the Young's modulus, and the spring constant. Okay? Because they're both, values that represent how stretchable something is. Again, they do have different units. The Young's modulus having units of force per area, whereas the spring constant has units of force per length. And to say it one more time, that's because the spring constant was dependent for every individual spring. Young's modulus instead defines an entire material. Okay? And usually under certain operating conditions like a temperature and so on. Okay? So that's it for the Young's modulus or elastic modulus. And elastic modulus is even evoked here in the letter E, because after all, it is the elastic behavior of the solid. Then we have the shear modulus, represented by the letter G, not sure why. And the formula looks exactly the same, but do remember that here, the force is not perpendicular to the area, but instead parallel to the area. And so in kind of the meaning of delta L, and L can have different in the context of shear as opposed to elasticity. Okay? And the last one is the bulk modulus. All right? B for the bulk modulus. Notice the formula looks a bit different. Namely, it's got a negative in front. That's because every time there is basically a volume change, it's always going to be less. Whereas here, with both the Young's especially with the Young's modulus, you can stretch something, you can make it longer. You're not always compressing it. But in the case of the bulk modulus, you are always compressing it because pressure can't ever make something bigger. Okay? it's always going to make something smaller, all right? And so then we have the bulk modulus, and then we have that change in volume over the original volume, okay? All the same units though, because after all, force per area was pressure, all right? And this is a ratio, it's dimensionless, so it doesn't really matter that we're considering a ratio of volumes, it's compared to a ratio of lengths, okay? All right, so let's finally get to those practice problems, all right? So 3 types, just elastic modulus problems, shear modulus problems, and bulk modulus problems, all right? So first what we're going to do is an elastic one, and this is an interesting problem to start with. It actually has one extra kind of term or consideration, and let's read it and see where that comes from. So the length of paracord is not to exceed 400 kilograms in terms of its total loaded mass when being used for parachuting. If the maximum upward acceleration of the person parachuting is 7.8 meters per second squared, then what must be the diameter of the paracord? Assume a tensile strength of 500 times 10 to the 6 newtons per square meter, all right, and a safety factor of 7.5, okay? So the idea here is we have maximum stress is ultimate strength divided by the safety factor. Because remember, ultimate strength was that maximum value on the stress strain graph, okay? The safety factor is a way to relate that to the actual maximum stress, okay? Both maximum stress and ultimate strength have units of, you know, newtons per square meter. The safety factor is just a dimensionless ratio to relate the two, okay? All right, so hopefully that makes sense. Here's the picture, all right? We want to consider a free body diagram to make sure we understand what it means to have the upward acceleration. So we're to define positive y as upwards. The tension force exerted by the parachute once it's opened on the person we'll call Ft, and then obviously gravity is also exerting a force on the person. So then we have our sum of forces, tension minus gravity equals ma. Why is a positive? Because when the parachute is first opened, what direction is the person accelerating? Up, right? Because the idea is they were traveling at some maybe terminal velocity before they opened their parachute. They open their parachute and they slow down dramatically. That means the acceleration has to oppose their downward velocity. Acceleration must be up, okay? So hopefully that makes sense. All right, so we'll go ahead and solve for the tension. Here we're going to plug in the maximum acceleration we're given. Fg is going to work because we have our, basically our rated mass that the parachute and the paracord can handle of 400 kilograms. All right, so then we just factor out that m. Again, that's going to be the 400 kilograms. Okay, so then we'll hold on to that because we're going to need that to plug into this formula here. Okay. So maximum stress then is just going to be the tension divided by the cross-sectional area of the cord. That's going to be equal to the ultimate strength over 7.5. All right. And so then we'll plug in for here, we're just replacing the force with what we got from our free body diagram, the mass that the paracord is rated at, gravity plus 7.8. Because the idea is when the person is accelerating upwards, the net acceleration that's driving the tension force is, or rather where the accelerations that are leading to the tension force is the sum of the two, okay? Because of course that makes sense. It's like when an elevator is slowing down, you're pushed into the ground. When the parachute is slowing the parachuter down, that's when it's under the most stress, okay? All right, and then obviously this is just going to be the formula for the cross-sectional area because we're treating it as a circular cross-sectional area. All right. And then here we have it equal to our ultimate strength divided by the safety factor, okay? Because then that'll then allow it to be equal to the maximum stress, okay? And so then I'm just going to solve for the radius, all right? Plug in all our numbers and we get 5.8 millimeters, all right? And since we were asked for the diameter, not the radius, we'll double it and convert it over to centimeters and get 1.16 centimeters. So that's the minimum thickness the paracord needs with this generous safety factor of 7.5. Okay, all right. Let's do another example. All right, so this is a type 2. Notice the coloring here. I didn't color them ahead of time, so obviously I'm using the highlighter to show the colors of red, light blue, and purple. So let's do a purple problem. That means a bulk modulus problem. So a cylinder of cork with a radius of 2 centimeters and a length of 5.5 centimeters has a bulk modulus of 1.05 times 10 to the 7 newtons per square meter. That's a low bulk modulus because cork is rather easily compressed, right? When this cork is dropped into the ocean to a depth of 8 kilometers, basically some deepest part of the ocean, what is its new radius? Okay, so we're going to find the hydrostatic pressure at that given depth. Okay, so we're just going to use the formula for hydrostatic pressure back from our chapter on fluids. Rho GH is the formula. We're going to, since we weren't given a value otherwise, we'll just use the density of pure water rather than salt water. All right, 1,000 kilograms per cubic meter, gravitational acceleration, and then 8 kilometers converted to meters. And we get a large pressure value, because there's a lot of pressure there at the very depths of the ocean, of 7.84 times 10 to the 7 pascals. All right. So then we're going to go ahead and solve for the ratio of the change in volume over the original volume. Okay. And that gives us a value of negative 7.46. Okay, because again, the change in volume here is actually, it would have units of cubic meters. The original volume would also have units of cubic meters. So this ratio just tells you by what factor did it change. And since it's negative, that means it shrunk, and it shrunk by a factor of 7.46. So that means that our cork here is, well, less than 1/7 its original size, right? So a dramatic decrease in its size. And that is a testament both to the incredible depth of the ocean and to the compressibility of cork. All right, so then if we want to find the new radius, we'll simply take the original radius and divide by that factor, again, because it's compression. And then we find that the new one is 0.264 centimeters, right? So instead of being 2 centimeters, it's about 1/5 of a centimeter. Well, I guess a quarter, right? So you go from 2 centimeters to about a quarter, right? But that makes sense because it's just a little bit more, it's almost an eighth, right? Which we see here, it's almost like we're dividing by 8, okay? All right, and notice we did not need the length because it was all just a fractional change, so we could have multiplied by any particular length in our object. In this case, it just happened to be the radius. Okay, so let's do another interesting problem here, maybe arguably more interesting than the last one. A large skyscraper, okay, with a huge weight here of 4.02 times 10 to the 8 kilograms. And then how much elastic potential energy is stored in the brick foundation of such a building? We're going to take the Young's modulus of the brick to be 14 times 10 to the 9 newtons per square meter. This is what you'd get if you looked up common Young's moduli or elastic moduli for materials. And the foundation's dimensions are 10 meters by 15 meters. Okay, it's a big block of concrete. And that concrete also has a depth of 1.9 meters. Okay, so it's pretty deep. So let's find out how much stored energy there is in that concrete. Okay, so we know, zoom in on this bit because it's smaller writing. We know that elastic potential energy for a spring is 1/2 kx squared. Okay, so basically we're going to take this and we're going to derive a new formula. And this is a formula that could be used in other problems, but we're going to derive it in this example. All right, and we're also going to use Hooke's law, and you'll see why. Right. By the way, that's what this is right here. This is just the relationship between force, the spring constant, and a change in length of the spring. All right, so that means that the spring constant is F over K. All right, so then I'm going to rewrite stored elastic energy to basically eliminate the spring constant, because the spring constant isn't appropriate for a material like concrete, right? Instead we need to incorporate the elastic modulus, not the spring constant. Okay, so now I've rewritten the elastic potential energy in something like a spring, or maybe any material for that matter, as 1/2 F times X. Okay, so this is a good general form of considering elastic potential energy, okay? And then I'm going to actually use the definition of the elastic modulus and the way it relates to stress and strain. I'm gonna rewrite it to substitute in for F. So I'm gonna eliminate F from my elastic formula, my elastic potential energy formula, okay? So here what I'm doing is I'm just rewriting F based on this definition here. All right, so we got a cross-sectional area, we got the elastic modulus, the change in length over the original length, okay? And then I'll write this in terms of X, all right? The reason I'm writing it in terms of X is because I already have my original formula in terms of X. That X must be the same as the length, or at least be related to the length. That's the only dimension we care about, the same dimension that we call the depth up above. All right, so I'm just clearing up the variables here by using X instead of L, okay? All right. And here I point out, they have to be the same thing. X and delta X mean the same thing, okay? And you might be like, wait, but X naught, isn't X more like X naught? Isn't it a fixed value? Well, no, because think about elastic potential energy. It's all about changing something, storing something. So here, this really is a delta X, okay? It's the final state, but you had to start at some rate of no compression. And so this X and delta X in the two formulas actually mean the same thing, okay? I hope that's clear. All right, so now we're in good shape to substitute this force back in. So all I'm doing is taking this expression here, AE delta X over X naught, and substituting it into F. And I'm also going to actually rewrite X as delta X. Okay. That way I have a delta x squared in the numerator. I'm left with the original x naught in the denominator. I got the AE and the 1/2 from just the fact that it is energy. Okay. All right. And so then for the skyscraper, we can then go ahead and find the change. All right. So I'm just setting up here. I'm just going to go ahead and find the change in x. So when I find the change in x, it ends up being 3.56 millimeters. All right. So then if I plug that back into the, basically I'm kind of doing it in 2 steps, right? So I set this up, and this is, again, it's a very useful formula. Okay. But I set it up and I say, okay, well, I can just find the values quickly by just, finding delta x. And once I have delta x, then I can just plug it back into this. And see, that's what I do here. I just take the gravitational force, the 1/2, right? And the reason I do that is because, I was given the force. So, it just worked out well to do it that way. Okay. And so, but again, you could have used this formula as well. They would get there since, one was derived from the other, they'll both get you there. Okay. And so there we go. We have about 7 million joules of stored energy in the concrete. Kind of fascinating to think about that. As everything sits on these, not very, concrete is not all that compressible, okay? But just having a bunch of weight sitting on things, there's actually a huge amount of stored energy at any given point, like in the ground, okay? All right, let's move on to one that actually involves the shear modulus. That was the idea of like moving the top of something to create a parallelogram. All right, so here is the appropriate formula to use with the shear modulus represented by G. All right, and let's read the problem. So in order to calculate the shear modulus of a cube, a force is applied at the top of the block parallel to the surface. The cube is measures 35 centimeters to a side, and the applied force is 1.24 times 10 to the 4 newtons. The displacement of the top of the cube is found to be 785 micrometers. Okay, that's a millionth of a meter. What is the shear modulus of the material of which the cube is made? All right, so we'll go ahead and solve for G symbolically, and then we'll plug in everything that we know. All right, so we know the force. We know this is very much a plug and chug. We know the cross-sectional area because it's just length times length on one of the sides. We know that the original length would have been none other than that same 0.35, so we can actually cancel out one of these. And then we're dividing by the change, the 785 microns, which becomes 7.85 times 10 to the negative 4 meters. And there we have it. There is our shear modulus for this particular material. Pretty reasonable value, actually. Okay, which is different than the next problem. So let's take a look. So I wanted to design a problem around one of these really fast centrifuges, but turns out we're going to find out that I guess centrifuges have to stretch more than I accounted for, or either have a wider diameter than I accounted for. And let's see why. So a centrifuge is designed so they can spin at 300,000 RPMs, right? So incredibly fast, and experience no more than a 1 millimeter extension in its arms. Okay, because it's spinning so fast that its arms would have to stretch out a little bit. Okay, so we want to only have 1 millimeter. The centrifuge is built with arms that are 6 centimeters long, a little on the long side, that's an issue, and they hold samples of that weigh 180 grams. All right. What must be the elastic modulus of the material used for the centrifuge arms? And what I meant to add to the problem, and I've added here after the fact, is that in addition to the arms being 6 centimeters long, we also need to know what their cross-sectional area is. So here I assume that they are, they're circular rods, and they have an 8 millimeter diameter. Okay. All right, so find the centripetal force. All right, and remember that for uniform circular motion, the velocity is the circumference times the frequency. Okay. All right, so then our centripetal force formula is mv squared over r. We'll substitute in for v using 2 pi rf. So then we have a 4 pi squared r squared f squared. That's going to cancel out one of the r's as I show here. And then we can go ahead and plug in all our values to get the centripetal force. And we get the incredibly large force of 138 trillion newtons, because a trillion is 10 to the 12. So 1.38 to the 10 to the 14 would be 138 trillion. Okay, so an unbelievably large force. All right. And then we're going to go ahead and actually use that force value and our other physical parameters of the centrifuge to calculate the Young's modulus or elastic modulus, plug in all the numbers, and we end up with 1.65 times 10 to the 20 newtons per square meter. Now, to be fair, it is possible to have elastic moduli that are in the order of 10 to the 12 newtons per square meter. Those are some of the strongest things, the least stretchable materials out there, but nothing is actually no common substance, nothing probably short of like a neutron star has such a high elastic modulus of 1.65 times 10 to the 20. So that means that nothing's that strong, we better go back and redesign our centrifuge because it's going to stretch more than 1 millimeter. Okay? All right. So let's look at our last example here, example 6. This one is about kind of interpreting a stress strain graph. Good way to finish off with kind of referring back to the key terms and some of the key ideas, which is a big part of this material because computationally it's not terribly difficult. The figure shows the stress strain curve for a material. The scale of the stress axis is set by the fact that S is 300 in units of 10 to the 6 newtons per square meter. This should be to the 6, by the way, right, raised to the 6th power. What are the Young's modulus, the approximate yield strength for this material, and the approximate ultimate strength? Also, what's the approximate toughness of this material? Okay, let's see. All right, so first of all, to find the elastic modulus, we simply look at the linear region and do rise over run. This is a good place to do it because it crosses one of our defined values here. And so then I know that I have a rise of 150 million newtons per square meter and a run of basically, well, 0.002, no units, because remember this is a change in length over original length. And so there we go. There we have our elastic modulus. And you can see it is quite common to have an elastic modulus on the order of 75 billion. Okay, so totally fine to have very large numbers, just not on the order of 10 to the 20. But 10 to the 10 is quite common for elastic moduli. All right, and then we're going to find for this one here, for part B, the approximate yield strength. This is the point where the linear slope ends. So I've kind of shown it here. There's not too much, right? Once the linearity ends, there's not much behavior afterwards, but there's a little. So we'll approximate it as 275 times 10 to the 6 newtons per square meter. The idea is that it's just a little bit below the 300 mark because S, after all, is 300. All right. And then the largest value of the stress reached, well, that we can say almost gets all the way up to the 300. So we'll say it's basically at 300 because C, after all, is asking for the ultimate strength. And the ultimate strength is just the high point. Even when it dips back down, all right, that doesn't count against the ultimate strength. The ultimate strength is still the greatest value on the vertical axis that's ever reached, even if the material starts to yield at the end and go back down on the stress strain graph. Okay? All right, so now let's consider this shaded area for part D, which is the toughness. Because remember, the toughness is the area under the curve. So the area under the curve is the toughness, with each block having an area of 50 times 10 to the 3 joules. And that's because the dimensions, the units of the area under the curve is none other than energy. Okay? Toughness is a measurement of energy. It's stored energy. All right? And so that way we can then say that the area is approximately equal to the area of a triangle. Again, not perfect, but pretty close. All right? So then it's 1/2 base times height. And so then what I'm doing here is I'm just taking 1/2 base times height. And the height we know is to be 300 times 10 to the 6, right? Because it's all the way up there. That's one of the values we know. And then we also obviously know this value here. Okay, and then that's this line, so that's why I added it. I said it's 0.0045 because it's a little bit past the 4 line. So there we have it. There is our stored energy, about 675,000 joules for this particular material. Okay, all right, well that concludes our last example. Hopefully you have a good idea of what stress strain problems look like and the 3 types of deformation. Okay, all right, well thank you so much for watching. I hope this video has been interesting and informative.